Good. Anyone has any questions? Are we close to the last chapter? Yes, we're very close. So actually, let's do this. What happened? Oh, okay. This is not what I want. Let me start again. Okay. So this is chapter 7. So we covered chapter 1, chapter 2, chapter 3, chapter 5, chapter 6, chapter 7 will be our last chapter. In chapter 7, we talked about 7.1 parametric equation. So what's the parametric equations? Parametric equation is basically x, a point x comma y. X is a function in terms of t, and y is a function in terms of t. So in this case, x and y are both related, are both represented with the same variable, with the same variable. So we know any function, right? Any function can be represented as a parametric equation. So x is x. What's y? Y is f of x. But we can do more than that, more than functions. That's why we build a structure of parametric equations. Like a circle is a parametric equation, right? Can be represented with parametric equations. X of t equals to r radius times cosine t, right? Y of t equals to r times sine of t. So parametric equations between x and y, you know, y doesn't have to be a function of x. The only thing is, so x is a function in terms of t, and y is a function of in terms of t. And of course, if we put x comma y, that's a trajectory, right? It will be a trajectory made by those two variables, x of t and y of t. So today we're going to talk about the calculus of parametric curves. Then we're going to cover polar coordinates. And we're going to talk about the area and arc length in polar coordinates. Okay. We're not going to talk about conic sections. Are we going to? I don't think so. I don't think conic section is on the syllabus. So yes, so answer James' question, we are very close. Right? So we are at the last chapter. We're very close to finish. And we are at the end of the semester, actually. Okay, any other questions? If not, let's talk about parametric curves. So 4 things involved. So first, we want to determine derivatives and the equations of tangents for parametric curves. We know some parametric curves are functions, but not all parametric curves are functions, like a circle. An ellipse are not functions, but we can still talk about its tangent lines, its derivatives. We will find out how. And the second part is we can find area under a parametric curve. And then we want to use the equation for arc length of a parametric curve. So we can find the length from one point to another point of the curve. And then apply the formula for surface area to a volume generated by parametric curve. So basically we see, so a parametric curve is a trajectory made by x comma y, and x can be represented as a function of t, and y can be represented as a function of t. This is how x and y related, because they're both related to variable t, so they are related. And let's see this example, right? We have this parametric equation, x of t equals 2t plus 3, y of t equals 3t minus 4. So both x and y are linear functions in terms of t. And we restrict the t goes from -2 to 3, including -2 and 3. And if we draw the graph, we get this. We still get a straight line. When t equals to -2, we get this point. So on and so forth. When t equals 0, we get this point. When t equals to 3, we get this point. So we get a line segment. Get a line segment for these parametric equations, right? If we want, because this is a line, right? A segment, line segment. If we want, we can rewrite this as a function. We can call the first one x, and the y can be represented as y of x or f of x. Right? Restrict the domain to be from -2 to 3. Just like this, right? So from x of t, we can solve for t, then we plug t into y. So you see that's a linear function, right? Y equals to 3x divided by 2 minus 17 over 2. So y can be represented as a function of t. So parametric equations just another structure, right? Another structure. So functions is just a subset. Functions as a subset, we can always write functions as parametric equations. There's something called a graphing, if you call it a graph. So first variable is x, second variable is f of x, right? So that's a parametric equation. So x of t equals to x, identity function. X of t equals to t, identity function. Then f of x can be represented as y of t. Okay. So with this parametric equation, if we want to take derivative of y, so we see y prime or dy dx equals 3 over 2. Right? So, but let's calculate x prime and y prime separately. Because we have x prime, x of t defined as 2t plus 2 plus 3. So x prime of t equals to 2. Right? And the y of t equals 3t plus minus 4. So y prime of t equals to 3. Right? If we do y prime of t divided by x prime of t, of course, we get 3 over 2. Right? So x prime of t equals 2, y prime of t equals 3. So dy dx equals dy over dt divided by dx over dt. So which equals to 3 over 2. So anyone has any questions? All right. So if anytime you have any questions, feel free to stop me. So theorem, derivative of parametric equations. Right? Consider the plane curve defined by parametric equation x is in terms of t as a function of t, and the y is a function in terms of t. Suppose that x prime and y prime exists, of course, right? So that's mathematically correct. But for this book, everything we deal with is x prime of t, y prime of t exists. And assume that x prime of t not equal to 0 at any t value, right? Because we won't be able to divide by 0. So we restricted x prime of t not equal to 0 at any point of t. Then the derivative of dy dx is just given by dy over dt, dx over dt, which is y prime of t divided by x prime of t. Okay. So this is the derivative, right? Y prime of t divided by x prime of t. Derivative. So we're going to skip this proof. Let's see examples. Finding the derivative of a parametric curve. So x of t equals to t squared minus 3, y of t equals to 2t minus 1, t goes from -3 to 4. So we take derivative with x in terms of t. Basically, you can think of dx over dt, right? Or x prime of t, that's equals to 2t. Y prime of t equals to 2. So dy over dx equals dy over dt divided by dx over dt. So equals to 2 divided by 2t equals to 1 over t. Right? So it's a function in terms of t. dy over dx is 1 over t. So of course the derivative is not defined when t equals 0. Right? If we calculate x of 0, y of 0, that gives us x of 0 equals -3, y of 0 equals -1, which corresponds to the point -3 and -1 on the graph. The graph of this curve is parabola opening to the right. And the point -1, -3, -1 is its vertex. Right? If we graph this parametric equation, x of t equals t squared minus 3, y of t equals to 2t minus 1. So y is linear, x is a of course, Jack, okay. If we graph it, we get this trajectory, right? We get this. So imagine, we go from this point, keeps going until 4, because until t equals to 4, right? Because this is graphed as x of t, y of t. So dy dx, so if we do dy dx here, 1 over t, so dy dx is the derivative at this point, right? Which is the slope of the tangent line. Well, what is the slope of a tangent line, a vertical line? Because this tangent line at this vertex is a vertical line. What's the slope of any vertical line? Undefined, right? Because x value is the same. If we do y2 minus y1 over x2 minus x1, we get a 0 in the denominator. So vertical line, the slope is undefined. So that's why here we see dy dx equals 1 over t, and t cannot be 0. If t is 0, it's undefined. You can see from this graph. At t equals 0, this point is tangent line, right? This tangent line is just undefined, so we won't be able to talk about dy dx. So B, x of t equals to linear, and y of t is a polynomial of degree 3, and t is restricted from -2 to 5. Same way we take the derivative, right? X prime of t equals to 2 because it's a linear. Derivative is just its slope. Y prime of t, we just take derivative as the first term, we get 3t squared. Second term, we get -3. Right. So we do dy dx, Then equals dy over dt divided by dx over dt equals to 3t squared minus 3 divided by 2. Right? You see, what's the beauty of this? The beauty of this, before, we know f prime of x, right? We know dy dx when it's a situation y is a function of x, right? We won't be able to talk about, because imagine a circle is not a function, right? So we won't be able to do that. So the beauty with parametric equation is now we have dy dx, right? X is a function of t, y is a function of t. We can always talk about dy dt in the rate of change of x in terms of y in terms of x. So we can talk about, you know, for circle, for ellipse, for any other curves, you know, who cannot be represented by functions. So that's the beauty of this. Right? So that's exactly why, you know, we need more structures than functions, because functions won't be able to cover all situations. Talk about a circle. So this derivative is 0 when t equals plus minus 1. Right? When t equals negative 1, we can plug in. We can plug in, right? X of negative 1 equals to negative 1. Y of negative 1 equals to 6. So a point on the trajectory would be negative 1, 6. And dy dx, we can substitute the value t equals to negative 1 in, right? Will be the rate of change at the point, will be the slope of the tangent line, tangent to this point, negative 1, 6. When t equals 1, we get another point, we get 3, 2, right? We can also plug into this dy dx, so that would be 0. When t equals 1, you see the slope is 0. So that tells us that's either maximum or minimum value, right? Because slope is 0, get a horizontal line as a tangent line. The point 3, 2 is relative minimum, and the point negative 1, 6 is a relative maximum. Okay, as seen in the graph. So if we graph the parametric equation for x of t equals to 2t plus 1, y of t equals to t cubed minus 3t plus 4, in the interval from negative 2 to 2, so we get this, you know, wiggles, right? Get these wiggles. And we see at t equals to negative 1, t equals to 1, we get relative maximum and relative minimum. When we get to the derivative at this point equals 0, we won't be able to tell if it's maximum or if it's minimum. But we can tell that's if the derivative is 0, we know the tangent line is a horizontal line. Any questions so far? Let's keep moving. So C, let's see this one. C will have x of t equals 5 cosine t, y of t equals 5 sine t, and t goes from 0 to 2 pi. Bingo. That's a circle centered at the origin with a radius of 5, right? So we take a derivative, x prime of t equals to negative 5 sine t, or y prime of t equals to 5 cosine t. dy dt equals y prime over x prime equals 5 cosine divided by negative 5 sine. So get a negative cosine t. Derivative is 0 when cosine t equals to 0. Right? Cosine t or sine t, if t is 0, sine 0 is not defined, right? Not sine 0 is not defined. Sine t equals 0 it cannot exist in this case, right? Dy dx, we cannot divide by 0. So we force sine t cannot be 0. So if sine t equals 0, that gives t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi, right, as critical points for t. So substituting when cosine t equals 0. So get those values. So t equals 0, we'll get those points. X 5, 5 comma 0 is a point, 0 comma 5 is a point, negative 5 comma 0 is a point, 0 comma negative 5 is a point, 5 comma 0 is of course the same as the first one. We see those 4 points. What are those 4 points? 2 are x-intercepts and 2 are y-intercepts, right? When the derivative is not defined, we know we have 2 x-intercepts, right? Because the tangent line is vertical line. Vertical lines, slopes undefined. And with 2 y-intercepts, right? When it's y-intercepts, we have the tangent line at this point, tangent to the point, are horizontal lines. So the slope is 0. So we get these 4 special points. Because we're going from 0 to 2 pi, so 2 pi is the same as 0. You see the question? Including 0, including 2 pi. That's why we have one more point which coincides with t equals 0. So at 2 pi and 0, the x value and the y value are the same. Yeah, we have those graphs, right? So we see we have this circle centered at the origin with radius of 5. T equals 0, t equals pi. Right, we get those 2 points. And the derivative at those 2 points does not exist, do not exist. Because the derivative at this point is the slope of the tangent line. And those 2 tangent lines are vertical lines. Vertical lines, right? We cannot talk about slope. Slope is undefined. At these 2 y-intercepts, the tangent line tangent to this point are horizontal lines. Slope is 0. Same thing for this one. Okay, let's all try this one, 7.4. We want to find the derivative. Right? We want to find the dy dx. And try to graph this. We'll try to locate the critical points. Well, let's all try. Let me try with you. So everybody try this one, 7.4. So we take a derivative with x in terms of t. Take a derivative of y in terms of t. Okay. Good. All right, so I get 3 critical points. What about you guys? I get at one point, the slope is undefined. The derivative is undefined. At 2 points, the slope, the derivatives are 0. Just give out the points. Yeah, okay, Shahara, t equals 2, t equals plus 1, negative 1. Yeah, so, but you have to calculate the points. Yeah, undefined at 2, yes, I get the same thing. What about the points? We have to calculate the points. It's true, one of them. So Paul, yeah, 5, 4, 4, negative. So x of 1. What's x of 1? X of 1 equals to 1 minus 4, negative 3, right? So at the point negative 4, 4, the slope is undefined. And at the point negative 3, negative 4, and 5, 4, the slopes are 0. Yeah. Should we do this together at the whiteboard? Or everyone is okay with this? Yes, negative 3, yes. Okay. So let's write down the question. Let's write down this function. So x of t equals t squared minus 4t. Y of t equals 2t cubed minus 6t. And t goes from negative 2 to 3. Let's go to the whiteboard. So what is the parametric equation is this. So we think about, and of course we can do 3 points, not 3 points. Yes, not 3 points. X, Y, Z, right? And we could do X, Y, Z more W. But here we only do 2. So X of t, Y of t. So we stay, we stay in dimension 2. Of course, we can do 3 dimensions, 4 dimensions, so on and so forth. So the beauty of this parametric equation is, it's sometimes it's more convenient than functions. Functions, a lot of times, is limited, restricted. So x of t is defined as t squared minus 4t. And the y of t is defined as 2t cubed minus 6t. All right. You see the beauty of this? X in terms of t, y in terms of t, we don't care about the relationship between x and y. There may be functions, there may not be functions, and in this case, we don't care. We don't care to make them, one to be a function in terms of other. But however, they are both related with t. So we can still talk about the dy dt, right? When we have a function, right, x, so every point is represented with x of x. And we can talk about f prime of x. And of course, f double prime of x if that exists, right? So that's the previous case. That's a previous case. But somehow functions are pretty tricky, pretty strict. Because you have to satisfy certain relationship to be able to talk about one variable makes a function in terms of the other, right? So it's limited. And with parametric equations, this is like a system, right? So we have this system of two equations. And we don't care about if x makes a function of y or y makes a function of x. X can be represented as a function, whatever the function is. Y can be represented as a function, whatever the function is. And then we can still talk about dy over dt. Let's still talk about the rate of change in terms of those two variables. Right? Just like when we talk about in this world. In this world, we talk about, so f of I prime equals to dy over dx, right? The rate of change. But a lot of relations are not functions, right? A lot of relations are not functions. So we can, and sometimes if we're lucky enough, we can represent both vectors, both variables in terms of the third variable. So in that case, we can still talk about dy dx. What's dy dx? Let's just dy over dt. Then, you know what, maybe I write this way. Did I use my... So this equals to dy over dt divided by dx over dt, right? So dy over dt divided by dx over dt is dy over dt multiplied by dt over dx, right? So simplify dt over dt, we got dy dx. So what's that? That's just y prime of t divided by x prime of t. Short notation, right? Just short notation. What does the y prime of t mean? Exactly means dy dt. In the rate of change of y in terms of t. So we just take derivative of x. So let's see, okay, x prime of t. Take derivative, the rule of taking derivative is exactly the same as before because x of t is just a function, x is a function in terms of t. This is a 2t minus 4. Power rule, right? Y prime of t equals to 6t minus 6. Power rule, right? Power rule. Then dy dt, what do we have? We get y prime, oh, 6t squared. You're exactly right. 6t squared. Thank you. 6t squared minus 6 divided by 2t minus 4. We can simplify a little bit, right? Because 2 is a common factor for everybody, we just divide by 2, so we get 3t squared minus 3 divided by t minus 3. So that's with mathematics, right? Whenever we can simplify, we just go ahead and simplify. So now we want to find all those critical points, right? So this is our dy dt. Rate of change of y in terms of x. In terms of x. So critical points. First, the whole thing dy over dx equals 0, right? When does dy dx equal 0? The numerator is 0, which means 3t squared minus 3 equals to 0. So we solve, we get t equals to plus minus 1, okay? And then another one thing is the denominator is 0. T minus 2 equals 0. So t minus 2 equals 0 give us vertical lines because the derivative does not exist at that point, but it still gives us like a critical point. It tells us something special. So t equals to 2. So now we get 3 values. We get a t equals plus 1 minus 1, t equals to 2. Now we just need to find all those points, right? So x of, let's find for positive 1. So x of 1 equals to 1 squared minus 4, which is just negative 3. Same thing, we want to find the y of 1. Y of 1 equals to 2 times 1 cube is 2, minus 6 times 1 is 6, so equals to negative 4. Then, when t equals to negative 1, get x of negative 1. Well, negative 1 squared is still 1, but the minus 4 times minus 1 becomes plus 4. So that equals to 5. And y of minus 1 equals to 2 times minus 1 cube. Minus 1 cube is minus 1, so we get a minus 2. Then minus 6 times negative 1 becomes plus 6. So we get a positive 4. So we get a second point. So the first point, I should write. So the first point is negative 3, comma, negative 4 at the t equals to 1. At t equals to negative 1, we get 5, comma, 4. So lastly, we have t equals to 2. So x of 2 equals to 2 squared minus 4 times 2 minus 8. So 4 minus 8, which is minus 4. And y of 2 is 2 times 2 cubed, which is 2 raised by 4, which is 16, minus 6 times 2, which is 12. So we get a 4. So we get our third point, negative 4, comma, 4. Okay, so we get 3 critical points. Anyone has any questions? Okay, let's go back to the book. Let's see this example. Finding a tangent line. We know the rate of change or the derivative at the point is the slope of the tangent line, right? Touching the point touching the graph or touching the curve. So this one, find the equation of the tangent line to the curve defined by the equations. So x of t equals t squared minus 3, y of t equals 2t minus 1, and t goes from negative 3 to 4 when t equals to 2. Okay, at this point. So first, let's find out this point when t equals to 2. So when t equals to 2, let's just do x of 2. X of 2 equals 2 squared minus 3 equals 1. Y of 2 equals 2 times 2 minus 1 equals 3. So we know the point is 1, comma 3. So the point is 1, comma 3. Now let's find the derivative. So let's find the slope of it. So we have 1 point. If we know the slope, we can write out the equation, right? So we need to find the slope. The slope is the derivative at the point. So how do we find it? We do y prime divided by x prime. So x prime equals 2t, y prime equals 2. So y prime divided by x prime, we get 2 over 2t, which is 1 over t. Right? So when t equals 2, dy over dx, we get a half. So the slope of the tangent line, slope of the tangent line at the point 1, comma 3 is half. We have a point, we have slope, we plug in slope point formula. So the y minus 3 equals to half times x minus 1. We can simplify this a little bit. The y equals to half x plus 5 over 2. So see, if we graph, we get this curve. This curve obviously is not a function, cannot be represented as a function. A function of x especially cannot be represented as a function of y in terms of x. If we turn 90 degrees, yes, we can represent it as a function of x in terms of y. So we graph will get this. So the tangent at 1, 3, the tangent line is this orange line. The slope is half. So with 1 point, with the derivative at this point, we can write out the equation of this tangent line, which is x over 2 plus 5 over 2. Okay, anyone has any questions? All right, now everyone, let's try 7.5. So we want to find a tangent line at t equals to 5. Okay. Okay, so 24x plus 100. I have different answer. Maybe I'm wrong. I have different answer. So let's see. X x of t equals t squared minus 4t. Yt equals 2t cubed minus 6t. And t equals to 5. All of you have that. So let's go to the whiteboard. I have different answer. Maybe I did something wrong. Let's see. So x of t, let's do x of 5. X of 5 equals 5 squared minus 4 times 5, that's 5, isn't it? Y of 5. Y of 5 equals 2 times 5 cubed. 5 cubed is 125. 2 times 125. Well, we'll see. 2 times 125 is 250. 250 minus 6 times 5, that's 30. 250 minus 30, that's 220. Right? So the point is, so now we get the point. The point we have 5 comma 250, 220. Now we want to find the slope. So y prime of t equals to 6t squared minus 6, right? 6t squared minus 6. So let's do y prime of 5. Y prime of 5 equals to 6 times 25, right? 6 multiplied by 25 minus 6. So how do I do that? I factor out 6. I do 25 minus 1, which is 24. So I have 25 of 6 minus 1 of 6. So I have 24 of 6. So 6 times 24. What's 6 times 24? 4 times 6, 24. 2 times 6, 20 times 6, 120. So 144, isn't it? So that's y prime at 5. So x prime of t equals to 2t minus 4, right? 2t minus 4. So x prime of 5 equals to 2 times 5 is 10, 10 minus 4, 6. 6. Oh, I made a mistake here. So, oh, hold on. 2t minus 6. 2t minus 4. I made a mistake right here. So x prime of 5 equals to 6. So here I got x prime of 5 equals to 5. Somehow I did 25. I don't know what I did. I did it wrong. I plug in the original one. So it's a 2t minus 4. So 2 times 5 is 10. 10 minus 4 is 6. Okay, I made a mistake. So y prime of 5 divided by x prime of 5 equals to 144 divided by 6, which equals to 24, which equals 24. Okay, now point slope formula, y minus 220 equals to 24 times x minus 5. Simplify a little bit. So y equals to 24x. 24 times 5, that's 120. 120. Beautiful. You guys did a wonderful job, and I have made a mistake. Okay, anyone has any questions? Great. Good job, guys. Okay, now let's keep moving. Second order derivative, of course, you know, if second order derivative exists, we can keep taking, we're treating x prime as a function, the x prime of t as a function of t, then we take a derivative with that. And for y, same thing, right? We're treating y prime of t as a function of t, we take a derivative with that. So that would be second order derivative. Then when we divide, we get a second order derivative of y in terms of x. Let's see this example. So we want to calculate a second derivative, d squared y over dx squared. And given x of t equals t squared minus 3, y of t equals 2t minus 1, t runs from -3 to 4. You see in parametric equation, right? You see the domain is always restricted. So we have an interval as a domain. Right? So dy dt to the y prime divided by x prime. So what do we get? We get 2 divided by 2t. 2 divided by 2t, we get 1 over t. Right? Then we take derivative again. So d dt, dy dx, dx dt. Right? If you think, okay. So take derivative with this dy dx in terms of we're treating this dy dx as a function of t. Then we take a derivative of this. So which is 2 with this 1 over t, which is negative 1 over t squared, right? Negative 1 over t squared. So dx dt, dx divided by dx dt again, dx dt is 2t. dx dt is 2t. So when we divide the negative 1 over t squared divided by 2t, you get negative 1 over 2t cubed. Right? So get this. We get this. Huh? Okay. Okay. So let's go back again. So d squared y dx squared. It's this. It's a d over dt over dx dt of dy dx. Okay, let's think in this way. Let's better think in this way. So d square y, d raised by square y over dx squared is defined in this case as d dt. What does d dt mean? Means we're taking derivative in terms of t. T is a variable. So d over dt, we're taking derivative with t over dx dt. Actually, let me write like this. Let me write as d of dy dx over dx. Right? Let's write this way. So d of, so we're taking derivative. So think about d over dx. Well, this is even better. Okay, dy dx. Okay, if you want to take a look, I'm typing in the chat. Oh, yeah, you're not able to see it. So d squared y over dx squared, we can think as d over dx of dy dx. Because dy dx now is a function. So we're taking derivative of y in terms of x, right, with x. Then d over dx. What's d over dx? That's d over dt over dx dt. Right. All right. So basically, we're having dy dx, right? We're having dy dx. Well, dy dx is a function in terms of t. Even the notation is weird, dy dx. But dy dx is a function in terms of t. Right? If you want, you can think of the dy over dx of t equals 1 over t. Right? So dy over dx is a function of t. And when we talk about second derivative, we're taking derivative with x, right? We're taking derivative of this dy dx in terms of x, So how do we understand d over dx? Because the variable is t, it's not x. So what do? We think about d over dt over dx dt. Now it makes sense, right? Now it's everything, the rate of change is in terms of t. So in this case, right, so we take derivative, so d of dt with 1 over t divided by 2t. So we calculate, we get negative 1 over 2t cubed. Anyone has any questions? So this one didn't do the critical points. So when we do the critical points, we do the same thing, right? We set it equal to 0. That's to find the horizontal tangent lines. We set the denominator to be 0. That's to find the vertical tangent lines. So let's do this, 7.6. Let's find the vertical tangent lines and the horizontal tangent lines at certain points. So basically, we need to find those points where at those points we either have horizontal tangent lines or vertical tangent lines. We have to apply product rule or quotient rule. Hmm. Interesting. I don't know if I made a mistake. Hmm. I get irrational numbers. Okay, it's the same. Okay. Let's see if you get irrational numbers. Really? Shahaya, you get the same points as before? Okay, go on has. Oh, go on. You need to find the points. Locate any point. So you have the set. What do you have? 3t squared minus 12t plus. Oh, second derivative. You shouldn't have x in it. You should not have x in it. Let's go to the whiteboard. So we have calculated before the first derivative for dy dx. Let me just write here. So x prime of t equals to 2t minus 4. 2t minus 4. Y prime of t equals to 6 times t squared minus 1. I see. Okay. So dy over dx we already calculate. Well, let's put of t in here, okay, to tell us dy dx is just a notation. It's a function of t. So what it is a 3 of t squared minus 1 divided by t minus 2, right? So we have this. Now we need to take derivative with this one. Oh, let's use blue color. So what do we want to do? We want to take, so this is just a function of t. And we want to take derivative in terms of t. So we want to do dt, ddt. We want to take derivative of this function, right? We want to take derivative of this function. So how do we take derivative of that? I can write like this. I can think of this function as, oops. You could use by product rule, quotient rule. I don't want to remember quotient rule. So what I want to do is I want to do 3 times t squared minus 1 times t minus 2 raised by negative 1. Right? So I can do product rule. Excuse me. So I take a derivative of this. When I take a derivative of this, I'm going to leave 3 outside, right? Outside the differentiation. So I'm going to get equals to 3 multiplied by, well, let's use this bracket. So I'm treating t squared minus 1 as f. So I'm taking derivative of f prime. So that's going to be 2, right? T squared is 2, or 2t. T squared, I'm taking derivative, that's 2t. 2t times t minus 2 raised by negative 1. That's my g, right? So I have f prime times g plus f g prime. So f is just a t squared minus 1 and g prime. So what is the g prime? G prime first is negative 1 by power rule. This is negative of negative times t minus 2 raised by negative 2, right? So the minus sign I'm going to put over here. Multiply by t minus 2 raised by negative 2. All multiplied by 3. So everything is with 3, right, with a factor of 3. Now I simplify a little bit. Look at this equals to 3 times I did something wrong. 2t times t minus 2 raised by negative 1, right? How do I get negative 2? Then minus t squared minus 1 multiplied by t minus 2 raised by negative 2, right? So now I have 3 times 2t over t minus 2. Then the other one is t minus 2 squared. So I'm going to multiply 2t with t minus 1, common denominator. Then minus t squared minus 1, t squared minus 1, right? All divided by t minus 2 squared. T minus 2 squared. So what do I get now? So that equals to 3 times, or what's in the numerator? 2t squared minus t squared, that's t squared. Then 2t minus nothing, that's just minus 2t. Then minus negative 1 becomes plus 1. Right? Then divided by t minus 2 squared. So t squared minus 2t plus 1, that's just t minus 1 squared. T minus 1 squared. Right? Then I divided this one, so I need to find out d squared y divided by dx squared. That's d over dt over dx over dt of dy dx of t, if you want to think as a function, right? Think dy dx as a function of t. So that just equals to whatever I have there, which is 3 t minus 1 squared divided by t minus 2 squared, then divided by 2t minus 4, which is 2 times t minus 2 cubed. Let me know if I have made a mistake. So now I want to find the critical points. So critical points, by setting the numerator to be 0, I get a t minus 1 equals 1, right, from the numerator. So numerator, I have 3 times t minus 1 squared. I set to be 0, so I get one solution, t equals 1. T equals 1, I get horizontal lines, right? For horizontal tangent line. But only one, so it's a tangent line. Or a horizontal tangent line. So that's t equals 1. Because I'm setting the numerator to be 0. In the second derivative, oh, what I'm talking about? I'm not talking about these lines anymore. Okay. Because this is second derivative. Basically, this is finding, what do you call it? Reflection points, right? So setting the numerator to be 0, I get t equals 1. Setting the denominator to be 0, I will get t equals 2. T equals 2. Now I just plug in back to x of 1, x of 2. X of 1, we already have it. That's why x of 1, y of 1, we already have it before. Let me just write down. So x of 1, y of 1 equals -3, -3, -4. Oh, that's exactly why the higher I have the same points. So -3, -4, but we don't have plus minus 1, so we only get this 1 point. -3, -4 is a reflection point, and t equals 2, -4 and 4, -4 and 4. So we have these two critical points. So only two critical points. If I did everything right, provided I did everything right. So we don't have the other point, 5, 4. Anyone has any questions? Okay, so this is about to remember the definition of d squared y over dx squared, which is considering, okay, which is considering, I think the key is this. Once we find a dy dx, we think about dy dx is just a function of t. just a function of t. So we take a derivative of this function in terms of t. Then we divide by dx dt, which is x prime of t. So this, I think it's just remember this definition. All right, let's go back to textbook. So this is integrals involving parametric equations. So how do we find the area under a curve defined parametrically? So let's see this one. X of t equals t minus sine t. Y of t equals 1 minus cosine t. All right, so we get this periodic, graph. So if we want to find the area under one curve, let's see, this is from 0 to 2 pi makes one period. So derive a formula for the area under the curve defined by this. We do the same thing, we approximate, right? From a finite world of approximation, approximation, we divide into n parts. Then we take a limit of the finite n parts. We let the n parts run to infinity parts. So we come with integral. Well, what's that? This is y of t times x prime of t. Right? So theorem. If we have a parametric equation, x of t, y of t, t runs from a to b. So a is the lower limit, b is the upper limit. And of course, assume x of t, y of t are smooth functions, which means differentiable at all values of t from a to b. The area under this curve is integral from a to b, y of t times x prime of t. Okay, y of t times x prime of t. Let's go back a little bit to see why. So we want to approximate, right? So we see the two dimensions. We see all the rectangles, the two dimensions, right? So we have this x of t1 minus x of t naught for the first one. So of course multiply by y of t, right? The height is y of t. The length is x of t1 minus x of t naught, so on and so forth. Then okay, if you want to really understand, you can just go through these proofs. Okay, for us, let's just try to remember this. This is y of t, the function, the y of t, right? The height multiplied by x prime of t. Then integrate from the lower limit to the upper limit. Okay, so that's it. So area under parametric curve. So consider the non-self-intersecting plane curve defined by the parametric equations x of t and y of t. T goes from a to b, and assume, because we'll only take a derivative of x, so assume x is smooth or it's differentiable at all values of t from a to b. The area under this curve is given by the integral from a to b, y of t multiplied by x prime of t. All right, let's see an example. So x is defined as t minus sine t, y is defined as 1 minus cosine t, and t runs from 0 to 2 pi. So we set up an integral. So from a to b, from 0 to 2 pi, and y of t is 1 minus cosine t, while x prime of t will be 1 minus cosine t, right? So 1 minus cosine t times 1 minus cosine t, you get a square, 1 minus cosine t squared. So which is 1 minus 2 cosine t plus cosine square t. Then we take derivative with this. So derivative of 1, y becomes 3 over 2. Oh, because we have half here. Okay, so 1, just 1 minus 2 cosine t. So we can integrate 1. We can integrate negative 2 cosine t. But how do we take an antiderivative of cosine square t? We want to use half angle formula, right? Half angle formula says cosine square t equals 1 plus cosine 2t over 2. Right, which is from double angle formula. Double angle formula, cosine of 2t, remember, equals 2 cosine square t minus 1. So this is from there. So cosine square t equals to 1 plus cosine 2t divided by 2. So 1 plus is half, 3 halves, minus 2 cosine t, then plus cosine 2t over 2, right? Plus half of cosine 2t. Now we can integrate all 3 terms. So integrate 3 over 2, get 3 over 2t. Integrate the negative 2 cosine t, that's negative 2 cosine t. Then cosine 2t integrate, right, that's half of sine 2t. Half times half of sine 2t, that's sine 2t over 4. Then we evaluate from 0 to 2 pi. Right, sine t at 2 pi, remember 2 pi is 0, right? So it's 0. And sine 2t, which is sine 4 pi, which is 0. Sine 0 is 0. Sine 2 times 0 is still sine 0, still 0. And so we only have the first one, 3 2t over 2. So 3 pi, t equals 2 pi, we get 6 pi over 2, which is 3 pi. Only the first term survived. So the area from 0 to 2 pi for this curve, that's a 3 pi. So let's go back to the picture. That's this picture. So from 0 to 2 pi, the area under this curve is 3 pi. Okay, 3 pi. How did we calculate it? We just follow the formula, right? So y of t multiplied by the derivative of x. Then we integrate, right? Y of t times x prime of t. Then we integrate. Anyone has any questions? Okay, let's practice. Let's see if we have time to practice. Almost 30. I'm going to skip the practice, okay? Arc length, right? We can always find arc length of a parametric equation. Let's just go ahead and jump to the formula. So we have parametric equation x of t, y of t. T runs from t1 to t2. So with the length from t1 to t2 would be integration from t1 to t2 square root of dx dt squared plus dy dt squared. That's very obvious, right? So we approximate with the triangles, right? So square root of x prime of t squared plus y prime of t squared. So x prime squared plus y prime squared, then square root. It's kind of obvious, right? Kind of obvious. We don't have to go through see the picture. So we just imagine we just zoom this in, right? At every point, we think right triangle. X prime of t is one leg, y prime of t is another leg. So we add the square of 2 legs, then we take square root, That's the hypotenuse, right? That's hypotenuse. That's the length of this. So that's the idea. So let's just follow this formula. So let's see an example. So x of t equals 3 cosine t, y of t equals 3 sine t. We want to take derivative of both. So x prime will be negative 3 sine t. Y prime of t will be 3 cosine t. So we plug in. We get negative 3 sine t squared plus 3 cosine t squared. Right? T goes from 0 to pi. So t goes from 0 to pi. Then we square root of both sum of two squares. We get 9 sine square t plus 9 cosine square t. Factor of 9. Sine square plus cosine square equals 1. Square root of 9 is 3. So 3 constant. So we just get 3 times pi. Get 3 pi. So the length for this one is also 3 pi. Right? It coincides with the area we just found. But those two have no connection, sorry. So the length from 0 to pi for this parametric equation, 3 cosine t, 3 sine t, is 3 pi. Well, let's think about it. What's 3 cosine t? What's the trajectory of x and y will make? It's the circle centered at the origin with radius of 3, right? So think about a circle with radius 3. What's the, from 0 to pi, it's like a semicircle. What's the circumference of a semicircle? Remember 2 pi r? So 2 times pi times r. R in this case is 3. So for whole circle, the circumference is 6 pi. But for half of it, it's 3 pi, right? So that's from algebra. But from here, we also find for half of the trajectory, for half of the curve from 0 to pi, the curve length, the length of the curve is 3 pi. Right? So this is just a fancy way find the circumference of a semicircle with radius of 3. Anyone has any questions? Okay, let's see if we have more. So you see, right, the graph of this is just a circle centered at origin with radius of 3. And what's the circumference of this semicircle? That's 3 pi. Okay, surface area generated by a parametric curve. So the formula is similar from before when we learned the disk method or washer method. So we can think as 2 pi r multiplied by the h, right? So 2 pi r is the function value f of x. That's before, right? Then h is square root of 1 plus derivative square. That's when we do before. Find, so washer method, find the area, find the surface area, right, before from the function. Now we can think the function as a parametric curve. So x of t, y of t. And then the formula becomes 2 pi, well, we have lower limit, upper limit, y of t, the height, multiplied by the second dimension, right? So we have y of t as one dimension, dt as another dimension. So the middle dimension is this, square root of x prime squared plus y prime squared. What is that? That's the length of this, right? It's the length of this. That's what we just had. Find the length of the curve, right? So this part is the length of the curve. So basically the height of this, right? Because each one is a circle. Each one is a circle. So the circumference is just 2 pi r. So I have 2 pi r. 2 pi and r is y of t. Y of t. Then how many of these circles, right, piled up? So the height of this is the square root of x prime of t squared plus y prime of t squared. Let's see an example. So this is find the surface area of a sphere, right, of a sphere of radius r centered at the origin. So sphere, we have 2 dimension is x equals r cosine t, y equals r sine t, and t runs from 0. So think about the curve, right? T runs from 0 to pi. Think about this. Then the surface area equals to 2 pi from a to b, y of t, square root of x prime square, y prime square dt. So we take a derivative of x, we get negative r sine t, take a derivative of y, we get r cosine t. We square the square root, we see that's just r, that just becomes r. So we have r, y of t equals r sine t, so r sine t times r is r squared sine t dt. Take a derivative of that, because, okay, t is a variable, okay, r just some number. So t is a variable, because we have dt. dt tells us t is a variable. So take a derivative, we get negative cosine t, evaluate from 0 to pi. We get 2, right? Because cosine pi is 1, negative 1, negative 1, that's positive 1. Cosine 0 is 1, 1 plus 1 is 2. 2 times 2 pi r squared is 4 pi r squared. So the surface area of a sphere with radius r is 4 pi r squared. Okay. Anyone has any questions? So this is follow the formula. Okay. We have parametric equation. Think about the curve. Oh, sure. Let's go back. Okay. So we start with a curve defined by the equation. Let's see why we need a curve. You see here, this formula. This formula is defined by the surface area. It's made by a, how do I see? Oh, okay. Let's go here. Actually, let's go here. So imagine this. So back then, imagine we do this, right? So we consider this line, this red line, as a function f of x. F of x, that's before, right? If we want to find the surface area of this one, so before we get this, we get 2 pi r times the height. How do we find the height? It's the square root of 1 plus derivative of f prime of x squared, right? So the idea is very similar. Idea is similar than before. But now, instead of considering this as a function in terms of x, we consider this as a curve. All right, so x of t, y of t. X of t, y of t. In that case, imagine in this, for this particular case, what's x of t? That's just a t. What's y of t? That's just f of x, right? Imagine x, comma, f of x, right? This is t, comma, f of t, right? We can treat it. So any function is a parametric equation with the first one to be identity. The second one is a function in terms of the first one. So the idea is from function word to parametric equations. So we represent the first one with x prime, with x of t, the second one with y of t, right? And we still can think about dy dt. right? That's y prime over x prime. And then how do we find the surface area? We want to find the circumference of each circle, right? We want to find the circumference of each circle. Then we just add up all those circles, all the circumference of circles. Because just imagine this one, this one, this one, this one, this one, there's infinite many, right? Just add up. So, okay, here, a surface of a revolution generated by a parametric curve parametrically defined curve. Okay, as you can imagine, that's x comma f of x, exactly the same as before, just notation-wise is different. Remember this here, right? F prime of x in parametric equations dy dx. What's dx in parametric equation? That's dy dt. That's dx dt, right? Dx dt. If you want to write down on your notebook, you could write the square root of 1 plus f prime of x square dx. You can rewrite this one. You can rewrite this one as a square root of 1 plus dy over dx squared. Then dx over dt. Dx dt outside, because dx is dt, right? Dx is dx dt in terms of t. Then you see here, you can, so inside the square root, 1, you can change 1 to be dx squared. So you have dx squared plus dy squared over dx squared. What's the square root of 1 over dx squared? That's just dx. So dx over dx becomes 1. So you have dt. So those two equations are exactly same. So this one exactly same as this one. Just in this one, just consider f prime of x as dy over dx. All right. Then consider dx as dx over dt. Then you can do the calculation, you get exactly this one. So for us, we just apply that, okay? We just apply that. We just apply, we have y of t, what's y of t? Y of t says r sine t, right? 2 pi, and go from 0 to pi, r sine t, y of t is r sine t, then square root of x prime is negative r sine t, y prime is r cosine t, right? So we just do 2 pi, y of t is r sine t, lower limit 0, upper limit pi, square root of x prime of t, which is negative r sine t square, y prime, which is r cosine t square. But when we square, we simplify sine square plus cosine square equals 1, square root of r square equals r times r square sine t. Well, r square just a number, right? This is a function of t, sine t is a function of t. What's antiderivative of sine t? We get negative cosine t. Evaluate at 0 to pi, we get 2. So 2 pi r squared times 2, we get a 4 pi r squared. Does that help, Damon? Okay, I think what's confused you is the equation probably. Is a formula, this formula. Just follow this formula, right? Plug in y of t, plug in x prime t, plug in y prime of t. And where does this come from? This comes from here, in function sense, all right? If y can be represented in terms of x in function sense, so those two equations will be exactly the same, those two formulas. But this one has a wider use, because we can use this for circles, we can use this for non-function curves. All right, anyone has any questions? So so we have a parametric equation. We deal with a parametric equation for now for 2 dimensions. Later on, you know, for if you keep If you keep learning mathematics, you could go to 3 dimensions, 4 dimensions. So with parametric equations, we can talk about, because parametric equations give us a trajectory. Normally it's a curve. It's a curve. So if it's a curve, we want to talk about at a certain point, the tangent line. We want to talk about the derivative at the point. We want to talk about how is y changing in terms of x change, the rate of change in terms of 2 variables. We can talk about that. So what is the derivative at the point? It's exactly the slope of the tangent line. So we can find the tangent line, right? So the first application. Second application, you give us a parametric equation. We can find out from one point to another point, the arc, the trajectory, the length of the trajectory, or the length of the curve, the length of the curve. So then also the length of a curve, under certain situations, it can form an area, and we can find the revolution forms a surface area, and we can find out the area of the surface area. So that's the 3 applications for parametric equations. Okay, anyone has any questions? I'm sorry, I have gone over time, sorry. How much of the final will be chapter 1 to 3? Oh, I don't really know. I would assume equally distributed. Oh, hold on. Because we have taken midterm, right? So I would think at least 60% of the material from the second part, 40%, at most 40% from the first part, which means the 40% from the midterm. How many questions are there in the final? I haven't made yet. But this time I'm thinking to make less questions. Because the first time, I think 20 questions are maybe too many. I'll make less questions. All right, any other, can you repeat again 40% for midterm and the rest is, right, at most, because we have taken midterm for the first part, so I'm considering to lower the grades. I mean, take a less percentage from the first part because you already have grades for the first part. But you let me know if this is a good idea or not. For the second part, so at least 60% from the second part. Okay. All right. So maybe we'll do 30, 70, or 40, 60. All right, we will see. Whichever is better for you guys. Those chapters were the worst. So which ones you are talking about? You're talking about the previous ones, the first part or the second part? Oh, 1, 2, 3 are the worst. Okay. All right. Oh, okay. All right. Okay. All right. Okay. Have a good night then. If you don't have any questions. One more question. Go ahead. Yeah, if you have questions, keep asking. I just don't want to hold you here. If you have no questions, you're free. So most questions would be from after midterm. Yes. Yes. If that benefits you. Do we know what topics specifically are going to be on the final, and should we just go off the syllabus topics? The syllabus topics, the homework, Jack, homework. Do your homework. You get credits for doing homework. You do homework to review for your final exam. Okay. Yeah, no topics, just chapters. Right. Focus on your homework. Do homework. Make up your homework. You still get grades. You still get credits for making up your homework. If we study now and focus on topics after midterm, right? Yes, but still, remember the midterm exam, right? I even give you solutions for the midterm. Make sure make sure you know the solutions. Okay, make sure if you take the midterm again, the same midterm again, make sure you can get full credits for it. Did you see you will lower percentage from midterm or for the final? No. Okay, Fujin. We are talking about since the first part 1, 2, 3 we have taken midterm, so maybe a lower percentage. So the final maybe only 40% from the first part, and then 60% from this part, from the second part. Does that make sense? Which means less questions from the first part. Okay, so midterm already covered chapter 1, 2, 3, right? So that means you already have grades for 1, 2, 3. So on the final will be less questions from 1, 2, 3. Does that make sense? Okay, all right. All right, you're welcome. Any other questions? Good night. Good night. Okay, great. Great. For those of you who haven't finished your homework, finish your homework. As long as you do 20 of them, if you're not late, you know, you already get 100% for homework. Okay. See you Thursday. I'm stop recording.